All right, so 2.4, we're going to be looking at polynomials today and finding zeros. So that essentially means we're going to get polynomials in standard form and we're going to be factoring them. That's our ultimate goal, is if I give you a polynomial that's a fourth degree polynomial, I want you to be able to factor this thing completely. And then using your factors, we're going to do the same work that we practiced doing in the last section, which was finding our zeros and figuring out what's happening at our intercepts. Before we get into all that, though, I want to talk about a couple of useful theorems that we're going to be using. So, polynomial remainder theorem and the polynomial factor theorem. You guys go ahead and read through those. I'm not going to read them out loud because it's kind of a mouthful. See if you can understand what they're trying to say there. For the polynomial remainder theorem. Is this making any sense to you?
Yeah.
Good. Good. All right, so rather than reword this, we're going to look at some examples, and then I'm going to ask you to come back and tell me what this means in English. I kind of did that for you for the polynomial factor theorem, but let's see if we can figure out what this thing means by doing an example together. So I would like you to take this function and find f of -3 for me. Go ahead and do that on your own right now. Use your calculator if you'd like to, but show me the work that you would do off to the side here. F of -3 equals, what would my Algebra 1 students do with this thing right now if I handed it to them? First of all, they'd freak out and say, to the third power, then there's 3 x's in there. We've never seen that before. But eventually, when I got them to calm down, they would say, well, it's the same thing we do anytime we're asked to find f of something. We take our function and we substitute in the value that we're told to substitute in. But once you get it written down, go ahead and use your calculator to work that out. We'll be efficient about this. My calculator's coming up with 35. Did I type it in right? Is that what you guys got? Woohoo! All right. Any questions on part A? Part B, they want us to find the remainder when we divide this thing by x over 3. So if you imagine that this has got a division symbol underneath it, and underneath that is an x plus 3, how would you do that? You could either use long division or synthetic division. What would your choice be if we're trying to do this quickly? Synthetic for sure? Okay, so go ahead and do that synthetic division for me right now. Let's get it set up. We're going to have our little box. This thing's the thing that's getting divided, so we'll put our coefficients here. Do we need to insert any zeros in this? Doesn't look like we're missing any terms. So we're going to have 1, 3, -11, and 2. Get everything set up, and then what goes in my little corner box here? If I'm dividing by x plus 3, what will go in this box? -3. All right, go ahead and do your synthetic division. Oh, that's nice. The question was asking what's the remainder when you divide it? The answer is 35. Do you think it's a coincidence that the answer to part A and part B were both 35? No, it's not. This, what we just did here, is what the polynomial remainder theorem says. If a polynomial f of x is divided by some factor, then the remainder, when you do that division, is going to be the same thing as if you'd plugged the value from that factor into the original function. So this is a shortcut for doing this. We did this in our calculator, but I'd say it was almost as fast for me to do the synthetic division to come up with this answer 35, even though I was pushing buttons in the calculator. Okay, so we'll use this in just a second. Last question here, part C. Is x plus 3 a factor of this polynomial? Yes or no? No. How do you know? Because the remainder was not equal to 0. That's what the polynomial factor theorem says. If something is a factor, then when you divide it, the remainder needs to come out to equal 0. Or in other words, if you plug that 0 into the function, you should get 0. So we're going to do this, rather than do it the way that we did originally, let's just do the synthetic division. I think the synthetic division is faster. So using the same function, so my coefficients are still 1, 3, negative 11, and 2. This time we're going to find f of 2. So let's put a 2 inside the box here. Do your synthetic division. Whatever comes out in the remainder box, that's the answer here. That's the number that you would get if you plug 2 into the function. So I did not just plug 2 into my function, but if I had plugged 2 into the function, what would I have gotten? I would have gotten 0. What's the remainder when we divide by x minus 2? 0. So is x minus 2 a factor then? Yes, because the remainder is equal to 0. This last part's really important. So I want to pause and ask if there's any questions up to here before we get into part G. Any questions in A through F? So kind of what I've just shown you is a trick that if you're trying to substitute a value into a polynomial, you can just do synthetic division with that value in the box here, and whatever's in the remainder is going to be your answer. This was a trick they used a whole bunch back in the day before calculators, because this is way faster. Can you imagine doing this by hand? And it would take a lot longer than doing it with synthetic division. And the other thing that we've reviewed, and this is probably old news to you, but if something is a factor, then when you divide it, you should get a remainder of 0. Last thing I want you to be aware of is that when we do synthetic division, we're actually getting more information than just whether it's a factor or not. We found that x minus 2 was a factor. X plus 3 was not. X minus 2 was a factor. If I take my original function, let me zoom out so I can see it. If I were to take my original function and factor that x minus 2 out, what would be the remaining factor that would still be in there after I factor that x minus 2 out? What is my remaining factor? You're right. It is x squared plus 5x minus 1. How do we know that? So that came from here. So we will be using this to factor polynomials. We're going to be using synthetic division to factor polynomials. And I need you to recognize that every time you do synthetic division and you get this 0, that you've created this new smaller polynomial that would be the result if you were to factor that thing out. This is called the depressed polynomial because it's smaller, not because it's sad. All right, we feeling okay about that? Let's go on. Let's go on. You guys remember the rational zeros theorem or the rational roots theorem? That's that P over Q list.
Oh.
Okay, so I hear people groaning right now, and it's probably because of what you had to do with the P over Q list. Making the P over Q list is not terribly difficult. It was the hunting through the P over Q list that was kind of a pain last year, more than likely. We won't be doing nearly as much hunting because we're going to be utilizing our calculator.
One of the test questions, 16, like factors on the PQ list, and you had to search through.
Yep, and you had to search through them, and if you got lucky, then maybe you caught it on the first try. There are also some tricks if you have to search through. Did you learn to like graph the points that you found as you were doing it and look for places where it would cross in between? So there are some tricks to that that we are not going to use too much, but I'll point them out if we get to them. Mostly we're going to be able to utilize the graphing calculators to take a lot of that guesswork out. Okay, but the P over Q list is still going to be a useful tool for us, so I want to go over it. This isn't going to be like our main source of information, but occasionally we're going to have to turn to this so that we don't have to do a whole bunch of guessing. Can you guys pause with this side conversations, please? Thank you. All right, so let's do it. So the P list comes from the factors of your constants. So my P list is going to be factors of 4. And it's positive and negative versions of each of these. I'm just going to put plus or minus out in front and do my list inside of curly braces. I don't get too picky about this. My factors of 4 are 1 and 2 and 4. Don't forget 1's a factor of anything. So that's my P list. My Q list is factors of your highest degree coefficient. So my Q list would be, again, plus or minus, and what goes into 6? 1 does, 2 does, 3 does, 4 doesn't, 5 doesn't, 6 does. So that's my P list and my Q list. From that, all I have to do is build a list of all the possible fractions that have one of these numbers on the top and one of these numbers on the bottom. And if you would like full credit when we do this on our test, put them in numerical order. Okay, so I'm going to make sort of a scratch version of this first. So I'm now building my P over Q list. And I'm going to make a long list here, and then I'm going to go back and put them in numerical order and get rid of any duplicates. So to make this easier for me, first of all, I know there's going to be 12 things on this list. 3 times 4. There's going to be 3 things with 1s in the bottom, and 3 things with 2s in the bottom, and 3 with 3s in the bottom, and 3 with 6s in the bottom. So 1, 2, 4, 1, 2, 4, 1, 2, 4, 1, 2, 4. All right, and then I'm going to go through and look for duplicates. And I'll just cross them out. Like 2 over 2 is a duplicate of 1 over 1, right? 4 over 2 is the same as 2 over 1. What do I got? 1. Yeah, 2 over 6 is the same as 1/3. These are the same, right? And 4 over 6 is the same as 2/3. I don't see anything else that reduces. It's usually things that reduce that'll give you duplicates. All right, so here's our P over Q list. We're going to put plus or minus out front. And then I'm going to just start building my list from least to greatest out of this. The smallest number on here is 1 over 6. What comes next? I think 1/3 is going to be next. And 2/3 maybe? No, a half comes before 2/3. 1/2 and then 2/3. I should really be checking these off as I go. 1 over 6. That's what I got so far. And then 1. I think 1's next, right? Because 4/3 is a little bigger than 1. 1 would be next, and then 4/3, and then 2, and then 4. I do want these in numeric order. Practice doing that as you're doing your assignments. Is this kind of coming back to you? It's sort of a tedious process, but this was the easy part. Then again, the reason that I heard some groaning a moment ago was your next step last year would be to go start hunting through these things and using synthetic division to see if any of those were zeros, right? And again, there's some tricks that we could use, but there are how many things in this list? 1, 2, 3, 4, 5, 6, 7, 8, but double that because positive and negative, right? So there's actually 16. And you know that there's 4 zeros, so if you got really unlucky, you might try 12 different options before you found one that worked, which is a pain. Or you could get really lucky and maybe the first 4 that you try are the right ones. We're not going to do that, though. But I do need you to understand what this is because this will become useful in a minute. So let me ask you some questions to see if we understand this or not. So I'm going to pick a number just randomly. Let's say -2. Okay, you guys tell me, is -2 a 0 of this polynomial? Is -2 a 0 of this polynomial? Yes, no, or maybe? Yes, no, or maybe? I'm getting a maybe. I mean, anybody else want to go with maybes? Well, we'd have to do a little bit of work to figure it out, but how do you know it could be? Because it's on the list, okay? What about -3? Is -3 a 0 of this polynomial? Yes, no, or maybe? No, absolutely not. How do I know that it's not a 0 of this polynomial? -3 is a rational number, right? And it's not on our list, so there's no way that it could be a 0 for this thing, okay? What about 5/6? 5 over 6, is it a 0 of this polynomial? 5 over 6, is it on our list? It's not on our list, then no, there's no way it could possibly be a 0 of this thing. What about 2i? Is 2i a 0 of this thing? No. 2i, is it a 0 of this thing? So remember what the rational zeros theorem says is this list contains all of the rational zeros that are in the polynomial. This only gives us a list of the possible rational zeros. Is 2i rational? No, so 2i could be a 0. What about the square root of 2? Could the square root of 2 be a 0 of this thing? Is the square root of 2 rational? No, so this list doesn't help us with square root of 2. This list only helps us to eliminate things that are rational zeros. Yes?
Sorry, I might have misheard. Did you say
2i could be a 0 for this polynomial. It could be.
2i is rational?
2i is not rational. This list does not help me with the question, is 2i a 0 for this polynomial? Okay, this list is useful too. When I give you something that's not rational, it could be or it could not be. The only way we would know is to do the synthetic division with it. This list will only help us with rational zeros. All right. So again, if I asked you the question, is 2 plus root 5 a 0 of this polynomial? My answer right now is I don't know if this is or not, because this list doesn't help me. I would need to actually divide this and see if it worked. Good. All right. So let's do a problem. You guys ready? This is going to be awesome. This is the fun part. Have your calculators at hand. I've got sort of a step-by-step guide up above here, but we're not going to waste time going through and reading that. We're just going to do those steps. So here we go. First of all, we haven't talked about this theorem yet, but I want you to look at this polynomial and predict for me how many zeros we're going to have for this polynomial. How many zeros do you think we're going to have? And the answer is that there are going to be 4. Whatever the degree of the polynomial is going to give you, that's how many zeros we're going to have. So it's a 4th degree polynomial. So we are going to find 4 zeros. Now some of them may be repeated, right? That would mean it had a multiplicity of 2 or of 3. But we're going to have 4 zeros, which means that we should be able to factor this polynomial into a version that has 1, 2, 3, 4 factors, 1 for each of those zeros. So our job is going to be to find all of those zeros. Let's begin by making a P over Q list, okay? Now I'm going to make an abridged version of our P over Q list for this. So this is a slightly different version of our P over Q list. I'm just going to make one big fraction and put all my factors of 9 on the top and put all my factors of 5 on the bottom. Okay, this will be enough for what we're going to need it for later on. So factors of 9 are 1, 3, and 9, and factors of 5 are 1 and 5. Now on a test, I'm going to ask you to actually list them out, but this is good enough for right now. At a glance, could you look at this and answer the question, is it possible that 3/5 is a 0 for this thing? Is 3/5 possible? Is negative 3 a possibility for this? Yeah, okay. So that's good enough for us for right now. Okay, what we're going to do next is something that you didn't have access to last year because you didn't have your own graphing calculator, but now we do. So we're going to graph this thing. We're going to graph this thing because we know from our work on Friday that if we find some x-intercepts, those x-intercepts can give us some of these factors and hence some of those zeros, right? So let's graph it and see if we can find some of those x-intercepts from our graph. That's way easier than hunting through a P over Q list, isn't it? I've learned that I always need to really carefully double check and make sure I type this in correctly because I've spent a whole bunch of time trying to do problems where it didn't work out so great. All right. I'm going to pause and make sure everybody gets an opportunity to graph this. I'm going to actually make a quick sketch of this as well. When you're doing these in your assignment, I would like you to make a rough sketch. Does everybody have it typed in? Okay, it appears on my graph anyways, it appears that I might have a 0 at -3. Are you seeing that on yours as well? Do we have a quick and easy way we could check and see if for sure there's a 0 at -3? We could look in the table, or there's another way we could do it. Second calc value. Can you guys all hit second calc value? The calc menu is under the trace. You got to hit second Calc, hit enter for value, and it will ask you for an x coordinate. You to give it the x coordinate, it'll spit out a y coordinate. I'm going to give it -3. What am I hoping I get back? If -3 is a intercept, if it's a 0, then I should get 0 back. Is it? You getting 0 back? Sweet. All right. Hey, guess what, guys? We found one of our zeros, and I know that I have an x-intercept at -3. It looks like this graph is bouncing off at -1. Check -1 for me. Do the same thing. Check second calc value. Ooh, I like that. So it is bouncing off at -1. So I found, now the fact that it's bouncing off means what about that as a 0? It's in there twice. It's in there twice. It's a multiplicity of 2. And then there appears to be some other x-intercept happening over here, and it looks to me like it's somewhere between 0 and 1. So it could be a fraction. So I'm going to use second calc value, and I'm going to make some guesses at some fractions. Now, do I just want to guess in the dark here? Give me some viable guesses for some fractions that would be between 0 and 1 that could be zeros of this thing. 1.5? There's no way 1.5 is going to work. Because 1.5 is 3 over 2, and 3 over 2 is not on our P over Q list. That's an excellent guess. If we were going to make guesses, that would be a fine guess to do, but let's not sit here and guess all day. Let's try and use, we did the work to find this. Let's pick here. What are the only 2 values that could potentially be between 0 and 1? 3/5 and I think we could make 1/5 would work also, but I don't think 1/5 does. 3/5 does. You've tried it. So this is why we're going to make our P over Q list for when we have to find these fractional ones. So I would try 1/5 and I would try 3/5, but since you claim that it works already, I'm going to just jump straight to that. Did you have a question? Yep. So 3/5 works. Cool. So that means we should be about finished here. All we need to do is make our factors. So we got x plus 3, we got x plus 1, 2 copies of x plus 1, and then we're going to have to decide what to do with this 3/5. It could be x minus 3/5, but if we put x minus 3/5, we're not going to end up matching our original function. Because our original function has a coefficient of 5 out in front, and it doesn't have any fractional coefficients. What's another factor that we could put in here that you could set equal to 0 and solve and get 3/5? Something without any fractions in it. Okay, that's going to give us a decimal though. X minus 0.6. Yeah. 3x minus 5. You're on the right track, but that would give me a 0 of 5/3. 5x minus 3, I think would work, wouldn't it? If you set that equal to 0 and solve, would you get this? Now let's backtrack a minute. I like the 3/5. Let's talk through because if you're not comfortable with what I just did there, another way we could tackle this is this. We could say x minus 3/5. But we need to check and make sure that the first and last term of our polynomial is what we would get, okay? If I were to multiply out the first terms for each of these factors, am I going to get 5x to the 4th? No, I wouldn't, would I? Okay, so give me an a value that I could throw in front here that would fix that. We could just stick a 5 out here. Now if I multiply the first term in every factor, am I going to get 5x to the 4th? Okay, let's check the last term. So if I multiply the first or the last term in each factor, so 5, keep track for me here. 5 times 3 is 15, times 1 is still 15, times 1 is still 15, times negative 3/5. What's 15 times negative 3/5? negative, I think it's 9, isn't it? Negative 9. Hey, it worked. All right, so either of these versions would be fine. So if we decide to go with this, then we're going to have to make a correction to our leading multiplier. I think if I were going to write my final answer for this, like on a test or something, I'd say x plus 3, x plus 1 quantity squared, and 5x minus 3 would be my final function. All right, any questions on that one? Kind of nice that we didn't have to go through and hunt for all that stuff, right? Isn't it nice being able to look at the calculator graph and see where our zeros are? All right, let's do another one. This looks like it's going to have 4 zeros as well, so let me set up my answer. 1, 2, 3, 4 zeros, and then there will also be 4 factors that associate with those 4. Like the last one, some of these factors and zeros could be repeated. Entirely possible. Oh, shoot. You know what I forgot to do, guys? Sorry, I want to go back and make sure that we did this right. What would be a quick and easy way for me to make sure that this is the correct factoring? I could graph this, and it should perfectly match up with the original graph, right? If I've done everything correctly, I could go back into y2. Since I've still got my original in here, I'm going to do this now before we move on. X plus 3, x plus 1 squared, and 5x minus 3. And I'm actually going to look at the table rather than the graph, because I'm lazy, and I'm not lazy. I'm in a rush, and I don't want to wait for the thing to graph. It takes forever. The table will come up really quickly. And if I look at my table and I'm seeing the same values in y1 as I am in y2, then I'm convinced that those are correct. That's enough for me right now, just to see that those y1, y2 values match. Okay, moving on to our next one. Do we need a P over Q list? Let's go ahead and see what happens. We don't always use the P over Q list, so let's graph it and see. Maybe all of our zeros will come out and be nice whole numbers, and we won't have to worry about fractional zeros. So let's graph this thing and make a sketch of it. 3x to the 4th minus 5x to the 3rd. 31. X squared. And then I'm going to double check that I typed that all in correctly, and we'll graph it. Come on, give me some integer zeros. Oh, I don't like that one. Bummer. All right, guys, I got bad news. We got some in-betweeners. One of these is promising. Are you guys seeing a 0 that might be an integer value? It looks like 3 maybe. That one looks like it could be an integer value. Test it. Do you remember how to test it? Second calc value, put in 3. Hey, all right, okay. We got 1 out of 4. We're a quarter of the way there, guys. All right, let's start making a sketch of this thing. So I've got 1 at 3. It looks like there's another intercept somewhere between 0 and 1, somewhere between 1 and 2, and then also one between -3 and -4. So this one's at 3. We got 3 others, though, that are kind of those betweener ones. So let's go ahead and make our P over Q list. Maybe there'll be something on our P over Q list that'll work. So I'm building my P over Q list. See, factors of 30 on the top. That's a lot of those. 1, 2, 3. Does 4 go into 30? No. 5 does. 6 does. 7, no. 8, 9. 10 does. 12, no. 15 does. And then 30. Whew, that's a bunch. Luckily, there's not too many factors for 3. It's 1 and 3. So the nice thing is we don't need to use synthetic division for these to test them. Well, let's see here. Let's see if we can find this one that's between 0 and 1. Mm-hmm.
Since none of the other integers are, none of the other zeros are full numbers,
Mm-hmm.
can we just cross out the 1 and the 1 and the 3?
Oh, you're saying we don't need this 1 down here because we know that none of those are. Yeah, you're right. You're right.
And we can also cross out all the factors of 3, right? Because those would all.
Anything that's going to divide by 3, yeah. There's definitely some stuff that we can ignore. So what fractions could we make that's between 0 and positive 1? We could make 1/3, we could make 2/3, 3 over 3 would be too big. 5/3 is, well, 5/3 could be this one, right? Because that's between 1 and 2. I'm focused on this guy right now. I think the only fractions we can make between 0 and 1 are 1/3 and 2/3. Let's try both of those. Hopefully one of them will work. 1/3 does not work. So when you do the second calc value, you can put in fractions. I'm trying 2/3 now. I'm just typing in 2 divided by 3. Come on, please work, please work, please work. Yes! 2/3 worked. Excellent. Okay, there's 2. We're halfway there, guys. All right, now I need something between 1 and 2. And I think the only fraction I can make off of this list between 1 and 2 is 5/3. Agreed? So if this doesn't work, I'm going to be very upset. Oh. 5/3 is not a 0 of this thing. We just tried plugging it in and it didn't work. What's that mean then? What does that mean about this 0? There is a 0 between 1 and 2, but it's not on this list, so that means that 0 must be, it's got to be irrational. It's going to have a square root in it, or it's going to be, well, it's not going to be imaginary because it is crossing here. It's going to have some kind of square root in it. All right. P over Q list is not going to help us finding irrational fraction or irrational roots. So from here, we're going to have to rely on our other skills. Okay, question?
Will the P over Q list handle like really weird decimals?
Yeah, anything that can be written as a fraction. So as long as the decimal is, well, anything that can be written as a fraction. Yeah. Which any decimal that terminates can be written as a fraction, right? Over 1,000 or 10,000 or 1,000,000 or something. Yeah. Okay, so here's what we're going to need to do. We're going to need to take this polynomial and we're going to do some factoring on it. Okay, so I'm going to write this off the side. I'm trying to leave myself some space here to do some synthetic division. I'm going to write my original polynomial off to the side here. 3x to the 4th minus 5x to the 3rd minus 31x squared plus 67x minus 30. That's my original polynomial. And I'm going to start factoring it. So every step of synthetic division that I do, I am going to factor this thing out a little bit. You do not have to show this step in your assignments, but I'm going to tell you this. You need to understand what's going on here. This is not If you start taking this as sort of a step-by-step process and you don't understand what you're doing when you're doing this synthetic division, you're going to run into some trouble later on in the unit, okay? This happens to my students every year. They're like, oh, you just do this, and then you do this, and then you do this. I need you to know what you're doing when you're doing that synthetic division, okay? So let's start with synthetic division, and let's factor out one of these two factors. I know that x minus 3 is one of my factors, and then I'm going to write this as 3x minus 2. I think if I set that equal to 0 and solve, I would get 2/3. Which one would you like to do? The one that's going to have the whole number in the box, or the one that's got the fraction in the box? Which would you rather do first? Whole number. Let's do the easy stuff first. Always pick the easy stuff first. So I'm going to do synthetic division. It's going to have a 3 up here, and then my coefficients for my original function were 3, -5, -31, 67, and -30. So I'll do my synthetic division here. And what am I expecting to get in my little box in the remainder box at the end? We better get a 0 in that box, right? Because if we don't get a 0 in that box, that means that this is not a factor, which means that's not a 0, which means we screwed up somewhere. So go ahead and do your synthetic division. You should get a 0 in that box. Let's see. 29, -19. 19 times 3. 57, but it'd be -57, so this becomes -10. Ooh, it's going to work. Wait a second. It's +10. Thank you. Whew. Okay, it worked. Hooray. All right, we're waiting for folks to finish up. I need you to ask yourself the question, what did you just do? What did you just learn? What did we learn? We confirmed that 3 is a 0, right? We definitely confirmed that. We confirmed that x minus 3 is a factor. We also found what we would get if we factored x minus 3 out of our original function. We would end up with the polynomial 3x to the, let's see, constant x squared, x to the third. 3x to the third plus 4x squared minus 19x plus 10. We found that depressed polynomial. All right, I got a high concept question for you here. This polynomial that I'm pointing at right here, can you name for me 1 0 of this polynomial? One thing that is definitely going to be a 0 for this polynomial. 3 is a wonderful guess, but I'm going to tell you that 3 is not a 0 of this polynomial. 2/3 is a 0 of this polynomial, yes. 3 is a 0 of this piece of it. 3 is a 0 of this polynomial. It's the only 0 of this polynomial. 2/3 is going to be a 0 of this. So when we factor out a factor, any other zeros that are left here are also going to be zeros of this thing. So as I go forward, I'm focused entirely on this. My last 3 zeros, this is going to have 3 zeros, right? Because it's got a third degree. The last 3 zeros of my original polynomial are also going to be zeros of this thing. And I know one of them is 2/3. So let's factor a 2/3 out of this. So I'm not going back to my original polynomial. I'm going to this depressed polynomial, which is nice because it's shorter. So every time you find a 0, you get your work becomes a little bit less in the next step. Now, what am I going to need to do? Remember to do when I get my final coefficients here. We talked about this when we reviewed synthetic division. When we have a fraction here, if I'm factoring out, if I'm trying to divide out 3x minus 2, I'm going to need to take all of these and divide them by whatever your denominator is here. We're going to need to divide them by 3. All right, but let's go through and do the synthetic division first. We'll remember to do that at the end. So 3 drop it down, 3 times 2/3. Remember, when you're doing this, take your number, divide it by the bottom, multiply by the top. That's the quick way to do it. 3 divided by 3 is 1, times 2 is 2. Together we get 6. 6 divided by 3 is 2, times 2 is 4. Add them together, we get negative 15. Divide by 3 and then multiply by 2. Divide by 3 is negative 5, times 2 is negative 10. And we get a 0 in our remainder, and we should have gotten a 0 in our remainder, right? That's good. So our actual coefficients then, if we divide everything by 3, is going to be 1, 2, and negative 5. So here's where we're at now. We factored out an x minus 3. We just factored out a 3x minus 2. And the factor that we're left with is now a second degree polynomial. It is 1x squared plus 2x minus 5. All right. Big concept question coming up here. You guys ready? Give me the universal sign if you need a moment to get this down. A couple people still writing. I'm going to wait because I don't want you to miss it. My question's going to be about this factor right here. All right. You ready? Tell me, what do you know about the zeros of this factor? What do we know at this point about the zeros of this factor? First of all, they are these two zeros, right? Whatever we're left from here, whatever we're missing from our zeros for our original polynomial, those are the two zeros from this factor. And what did we say about these two zeros a moment ago? Because we couldn't find it on our P over Q list, what did we say about these two zeros? They're irrational. Okay, so this thing has irrational zeros, which means it's not going to factor. So the only other way, well, there's two other ways I know to get the zeros out of this is what? Quadratic formula is one of them, and then completing the square is the other one. So essentially what we need to do now is we need to take that last factor, we need to set it equal to 0 and solve it. If you would like to do that by quadratic formula, go ahead and do that. If you'd like to do it by completing the square, go ahead and do that. I'm going to do my works on a side piece of paper here. All right, this is why we had that quiz at the beginning of the year, because you're going to be doing a lot of this in the last step. Six times 4. All right, we should be getting close here. If you don't have it yet, go ahead and write down -1 plus or minus root 6. Did anybody do completing the square to get it? Does this look easier or harder? Harder? I like it because the square root doesn't come in until the very last couple steps. Yeah, and it's good. Quadratic formula is good to, if you're comfortable with it, stick with what works. Okay, so we found our last two zeros are -1 plus root 6 and -1 minus root 6. All right, your textbook is going to ask you for different formats of your answer. One of them is going to be this. So this would be called our linear factorization. Let me write down what these last two factors would be. Or my last two factors from this would be x plus 1 minus root 6 and x plus 1 plus root 6. Do you see how I got those from those zeros? We just flipped the sign on both parts. Flip the sign on the -1 and flip the sign on either the positive root 6 or the negative root 6. And that's our linear factorization. So if they ask your assignment's going to ask for both of these in different parts. So if they ask for a linear factorization, we would say our factors are x minus 3, 3x minus 2, x plus 1 minus root 6, and x plus 1 plus root 6. When we're writing factors, we don't use plus or minuses. So you are actually going to have to write out both versions of those. If, on the other hand, they ask for a product of linear and irreducible quadratic factors with real, I think it says rational coefficients. Irreducible quadratic factors means they don't want anything with radicals in it. So the version they're looking for here would be what we had up here. So x minus 3, 3x minus 2. And this thing's irreducible. It's not factorable. So we would give that answer. Now, if they hadn't asked us for all of the zeros, we wouldn't have even had to go back and figure out what these last two were. We could have stopped right here because we would have known that anything that we got from this would have been irrational. All right, there's a lot of moving parts to this, guys. I want to pause for a second, and I want you to go back through kind of the whole process that we just went through there. Okay, there is kind of a step-by-step to it, but there's also a lot of little clues that we picked up along the way. And what I found is that people who try and memorize a step-by-step through this without kind of asking themselves those questions as they go along, what does this tell me? What does the fact that there's nothing from this list tell me about this zero? Those kind of questions end up struggling with this. And we're going to be doing this for the next, let's see, pretty much all of next week also. The only thing that's going to change in the next section is some of these are going to have some imaginary values in them as well. So I just want you to think through, what did we do? We looked at our graph. We hoped that we were going to be able to find some zeros on our graph, and we did. We found one. We found one that was nice and easy. Do you guys remember how we found this 2/3? We're like, well, there's something between 0 and 1, so let's make a list of all the fractions that we could potentially use, and we hunted through that. And luckily, we were able to find a second 0 from this. When we tried to find a 0 that was between 1 and 2, though, there was nothing on this. Now, I didn't go back and try and find another 0 between -3 and -4 because I know that if you've got one irrational 0, you're always going to have a pair of them. They always end up being conjugates like this. So at that point, I gave you a little extra information. I said these last two must be irrational. But we wouldn't have found anything on this list that would work for this one over here. So once we knew two of the zeros, we're like, okay, well, let's go ahead and start factoring those two factors out. right? Because I know that if I factor two zeros or two factors out of this thing, I can get it down to a quadratic. It started with a fourth degree, and I found enough zeros to factor and get it down to a quadratic here. And we got tools to deal with quadratics, right? We can use a quadratic formula, or we can use completing the square to find those last two zeros. So for right now, something that I can promise you is that if I give you a fifth degree polynomial, okay, if I give you a fifth degree polynomial, you're going to be able to find three of the zeros by looking at the graph. Okay, you might have to use a P over Q list because some of them might be some fractions. But I'm always going to give you enough, there will always be enough on the graph for you to be able to get it down to a second degree polynomial. You may have to finish up from time to time by doing the quadratic formula, but you'll always be able to find at least enough to get you down to a quadratic. If I give you a sixth degree polynomial, you'll be able to find four of the zeros from the graph, okay? Now, you may be able to find all six of them. In that case, it's a lot easier. We didn't have to do a whole lot of extra work on this. We were able to find all of our zeros straight from it. All right, you guys have any questions on that one? That's kind of our big problem for today. That's it. That's it. So we got 13 minutes. I highly recommend that you get started on the assignments. And I'm going to give you a suggested problem to start on. So let me pull the assignment up onto the screen here. Ooh, we got multiple problems here. Assignment 2.4 begins on page 223. Everything, those are all pretty straightforward. I would start with the last bank of problems, 49, 50, and 51. I'd see if you can get one of those at least going in class today. Those are the ones that are most like the last problem that we did. Everything up to there is just use the remainder theorem to find f of 4. That's simple. Here's two factors. Tell me whether this is a factor of this. How do you do that? You divide them and see if your remainder comes out to be 0. Yep. But I would start with 49, 50, or 51. Those will be the most complex. There are a couple problems from page 209 and 183, and then I did provide a full solution for number 183. I'm curious what that was. Oh, it's practice with completing the square. Yeah, that's not that big a deal, I don't think. All right, folks, I'll be around to answer questions, and then we got time, so I'm going to check your 2.3 assignment.